It's pretty wild to think about, when Einstein dropped his bombshell theory of general relativity on everybody,
Right.
it wasn't like the only game in town trying to figure out how gravity works. There were other folks out there with their own theories trying to explain, all those weird gravitational quirks that we see. But fast forward to today, and we've gotten so good at making super precise measurements. Like, we can actually see how the Earth's rotation kind of tugs on satellites. Like, it's crazy.
Wow.
And guess what? Einstein's predictions, they nailed it. Those other theories, not so much.
Really drives home how science works, doesn't it? Bit by bit.
Absolutely. It's a constant journey of discovery. And that's exactly the spirit we're bringing to this deep dive today.
It is, isn't it?
We're so excited to have with us Professor Lev Levitin. He's been at the forefront of what we now call quantum information theory, like since the beginning.
Yeah, for decades.
And, his collaborations with the likes of Norman Margolus and Tom Toffoli, those are legendary. And knowing your interest in all this, physics, information, computation, all tied together, we knew Professor Levitin's insights would be, well, essential. So our mission today is pretty clear.
Lay it on us.
We're going to dive deep into these interconnected fields led by Professor Levitin's expertise, and hopefully we'll stumble upon some of those, mind-blowing aha moments.
Who's those?
So Professor Levitin, maybe we could start with this. Your work covers a huge swath of information theory.
It does.
But it seems like the stuff that really made a splash had often came out of collaborations, especially with Margolus and Toffoli.
Absolutely, you're right.
What do you think it was about those collaborations that really resonated? Was it something about the work itself, or maybe the context, the timing? Who knows? What do you think?
I'm happy to share my perspective on this. It's interesting, isn't it? The work was certainly groundbreaking, but I think there's a human element intertwined with it that really amplified its impact.
Yeah, that makes sense.
Take the case of Tom Toffoli. Brilliant mind. He was the one who came up with the classical Toffoli gate. It's a cornerstone of reversible computing. And he also did, pioneering work on cellular automata.
Those are pretty cool, right?
Oh, they are. Simple rules that give rise to mind-boggling complexity. But here's the thing. Despite all his publications, the recognition he got from, everyone outside his institution, he was denied tenure.
Seriously?
Yeah, seriously. It was a huge blow. To me personally, to the field, it just felt like a blatant disregard for his contributions.
That's rough. So can we break this down a bit? What exactly makes reversible computing so special? And what's the big deal with the Toffoli gate?
Sure. It's all about information. You see, with typical computation, you lose information as you go. Think of an AND gate. If the output is 0, you can't tell for sure what the inputs were. They could have been 0 and 1, 1 and 0, or even 0 and 0. You've lost that initial data. But the Toffoli gate, it's different. It's reversible. You can always backtrack from the output to the exact inputs. No information gets lost. Theoretically, in a perfect world, you could do reversible computation with, 0 energy dissipation. Amazing, right?
0.
That's the idea. And then you have Toffoli's work on cellular automata. It showed how these incredibly intricate, lifelike patterns could pop up from super simple rules. It kind of hinted at, a deeper connection between basic principles and the complexity we see in the universe.
So it wasn't just the theory itself, right? It was almost like a moral issue, this injustice of how he was treated by the academic system. Even science isn't always a pure meritocracy, is it?
That's right. It can get messy. And unfortunately, Tom's story isn't unique. As Professor Levitin has often pointed out, academia can be, well, let's just say there are other forces at play besides pure scientific brilliance.
Right.
Sometimes it's politics, sometimes it's clashes over research directions, sometimes it's just personality conflicts. And talented folks get overlooked, even when their impact is obvious to everyone else.
It's a shame, really.
It is, and it makes you think, how do we really recognize and value scientific contributions?
Yeah, that's a good question, especially when you contrast that with your own experience, Professor Levitin, becoming an IE fellow. That was totally out of the blue, right? Just pure recognition at a conference.
That's right. I never went after it or anything. It just kind of happened organically. A bunch of colleagues, they valued my work and they put my name forward. It was incredibly gratifying.
That's awesome. I mean, it really makes you wonder about the role of chance, or maybe just being in the right place at the right time for how scientific work gets acknowledged.
Absolutely. I mean, look at Einstein. He was working in this, super fertile period for physics.
Yeah.
The turn of the 20th century.
Right.
Physics was riddled with these anomalies, things that didn't make sense with the old theories.
So the existing problems kind of primed everyone for some radical new thinking.
Exactly. It was a time ripe for revolution.
Yeah. And it's funny, isn't it? Einstein got his Nobel Prize for explaining the photoelectric effect, not for relativity directly. You'd think relativity would be the shoo-in.
You would, wouldn't you? I guess those ideas were so radical, so out there, that the Nobel Committee maybe wanted more concrete proof before giving him the prize for that specifically.
Makes sense. So we've got Einstein working on general relativity, right? But you mentioned there were other theories at the time trying to explain those same gravitational phenomena. What were those like?
Well, it's fascinating, right? You have Einstein's theory, super elegant, deeply theoretical, all about the curvature of space-time. And then you have these other attempts. Often they were more, like trying to tweak Newtonian gravity, add some bells and whistles to explain stuff like the wonky orbit of Mercury or light bending around the sun.
Right, so kind of patching up the old theories instead of a whole new framework.
Exactly. They lacked that, that deep conceptual shift that Einstein brought in.
It's interesting how that plays out in physics. There are these fundamental constants that describe the forces of nature. We've got the strong force, the weak force, electromagnetism, and, of course, gravity.
The Fab Four.
Right. And each of these forces has a dimensionless coupling constant, a number that doesn't depend on, what units you're using.
Pure numbers.
And for gravity, this constant is, ridiculously small.
Oh, it is. Like 10 to the power of minus 43, maybe even minus 47, depending on how you slice it.
Those are, ridiculously tiny numbers.
Well, they are, aren't they? Almost unfathomably small.
So how does that impact our ability to even test these theories about gravity if the constant is so small?
Well, it means when you're trying to calculate stuff, you get these infinite series of terms with higher and higher powers of this tiny constant.
And those terms get smaller and smaller, right?
Exactly. For the longest time, we could only measure effects that were proportional to the second power of the gravitational constant. Everything else was just too small to see. And here's the kicker. Some of those less radical theories, they actually matched Einstein's predictions up to that second-order approximation. So, for a while, it wasn't crystal clear that Einstein's theory was the only correct one.
So there was room for doubt.
Oh, definitely. But then, relatively recently, like in the 21st century, we finally got the tech to measure this super subtle effect.
Uh-oh, here comes the tech.
I know, right? But it's cool. It's the fourth-order effect of Earth's rotation on satellites. Tiny, tiny effect. And it lines up perfectly with Einstein. The other theories? Nope, they missed the mark.
So it took over a century to really get that definitive proof for Einstein.
That's science for you. Slow and steady.
Now, Professor Levitin, this kind of brings us to a question that's, at the core of your work. The nature of computation. Do you think computation is, baked into the universe, something fundamental like matter or energy, or is it something that just emerges under specific conditions from the interplay of matter and energy?
The big question, isn't it? And, as Professor Levitin has explored in depth, the answer might depend on how you define computation. If you're super broad about it, you could say, well, the universe itself is constantly transforming information, following its laws, like it's computing its next state from the current one. It's kind of a cosmic computation,
That's a pretty wild way to think about it. But what about examples like Conway's game of life? You've got these incredibly complex patterns coming from a handful of simple rules. Does that suggest that there might be, a pre-existing logical framework, something that was there even before the physical stuff?
That's a deep question, and some folks, like Tom Toffoli, they lean towards the idea of a fundamentally computational universe. There's also Wheeler's it from bit idea, which suggests that ultimately everything comes from information.
Right, it from bit.
But Professor Levitin, he tends to take a more grounded approach. He echoes Rolf Landauer's famous statement, information is physical.
Okay, so information itself has a physical basis. How does that influence your view of computation in the universe?
Here's the key. We can describe computation abstractly, right, with math, algorithms, all that.
Yeah.
But any real computation, it's got to happen in the physical world. And those physical laws, they set limits on what you can compute and how fast you can do it. It's not just a free-for-all. This idea is central to a lot of Professor Levitin's work, like the Margolus-Levitin theorem. It puts a hard limit on computation speed based on available energy. It shows that even these super abstract ideas, information, computation, they're bound by the real world.
It's like no matter how clever our algorithms get, physics has the final say.
Exactly. And this ties in with a question from one of our listeners. They asked, if simple rules can create so much complexity, like in the game of life, does that mean there's like a pre-existing set of rules governing the whole universe, like a cosmic rule book?
It's a great question, and Professor Levitin is very thoughtful about this. The game of life, it's a beautiful example of emergence, right? Complexity from simplicity. But we have to remember that game is still running on a computer, on a screen. Those rules, they exist within a physical context. Ultimately, they're rooted in the laws of physics as we understand them. So while it's super tempting to speculate about a deeper, maybe computational foundation for everything, we can't forget that the physical reality, the substrate, it's essential. The connection might be there, but it's not just an abstract game.
It's grounded in something real. Absolutely. And this leads to another fascinating idea from Professor Levitin. It's about how computation in our brains over vast cosmic timescales could potentially shape the physical fabric of reality. It's this poetic notion of, painting the galaxy with our thoughts. It's pretty mind-blowing, right?
It is. It's almost like our thoughts could have a physical impact on the universe.
That's the idea. Of course, this is pretty speculative. Our understanding of consciousness and the observer's role in quantum mechanics is still, a work in progress. But the point is, computation in our brains does lead to real changes in the world, even if not on a galactic scale, at least not yet. Just look at all the technology we've created, the infrastructure we've built. It's all a result of thought, of computation.
It's a testament to the power of ideas, for sure. But what about free will, then? You've mentioned that from your perspective, it might be more of an illusion than a fundamental reality. What's the thinking behind that?
I think Professor Levitin's view comes from the idea that our feeling of making free choices, it's kind of based on our limited awareness of what's going on in our own brains.
We don't have access to all that inner workings.
Exactly. We're not consciously aware of all the neural activity, the biochemical reactions that lead to our decisions. So it feels like a free choice, even though it might be the deterministic outcome of the physical state of our brain at that moment. It's like our brains are making the decisions and we're just along for the ride. This idea kind of ties in with some concepts in Kolmogorov complexity, which suggests that there are inherent limits to how much a system can know about itself.
So our brains are too complex for us to fully understand how they make decisions.
That's the idea. It's humbling, isn't it?
It is. Now, shifting gears a bit, you often talk about the density matrix in quantum computing. For listeners who might not be familiar, can you explain what it is? Maybe use an analogy from classical physics to make it clearer.
Sure. Think of it this way. In classical physics, if you're not totally sure about the exact state of a system, like you don't know the exact positions and speeds of all the particles, you might use a probability distribution. It tells you the likelihood of the system being in different possible states.
Right, like a range of possibilities.
Exactly. The density matrix in quantum mechanics, it's kind of similar. It represents our knowledge, or lack of knowledge, about the true quantum state of a system, especially when it's in a mix of different states. And here's a key point Professor Levitin makes. Even if you have a pure quantum state, described by a wave function, the density matrix you get from that wave function is the most complete description possible. There's no hidden information beyond that. It's got it all.
So it's like a probability distribution, but for quantum systems.
That's a good way to think about it.
Now, if you were talking to a student today, someone's super excited about information, computation, quantum mechanics, all that jazz, what areas would you point them towards? What are some of the big open questions that are still out there?
Professor Levitin is really fascinated by these fundamental limitations in quantum theory. They're called no-go theorems. Like you can't clone an unknown quantum state, you can't broadcast it, you can't perfectly distinguish non-orthogonal states. These are well established. But he suspects they might all point to a deeper principle, maybe something to do with the conservation of information at a quantum level. He's working on incorporating information as a fundamental concept in quantum theory, like rewriting the rules of the game. He thinks that could lead to some major breakthroughs.
That's ambitious. What about the practical side of things? Quantum computing, how do you see the progress so far? What are the big hurdles we still need to clear?
He's a bit cautious about what he calls pure digital quantum computing. He sees two main challenges. First, we need more groundbreaking quantum algorithms. We've got Shor's algorithm for factorization, Grover's search algorithm, but we need more. Second, it's really hard to isolate quantum systems from noise, from decoherence, while still controlling them precisely. It's a delicate balancing act. He also makes a distinction between true digital quantum computing and what he calls quantum analogous computation, which is promising for certain problems, but it's not the universal quantum computer that we dream of. He thinks solid-state systems, like quantum dots, might be a better bet for building robust, scalable quantum computers in the future.
So there's still a lot of work to be done.
Oh, for sure. Quantum computing is still in its early stages.
Now, a few years back, the Nobel Prize in Physics went to some amazing work that confirmed quantum non-locality. Can you give our listeners a quick rundown of what non-locality is and why it's such a big deal?
Non-locality. It's this spooky connection between quantum particles. You can have two particles, light years apart, and they're still linked. You measure something about one, it instantly affects the other. Einstein called it spooky action at a distance. We've confirmed it in labs over short distances. But extrapolating that to the entire universe, that's still based on the assumption that the laws of physics are the same everywhere, which is a pretty safe bet, but we can't test it directly across those vast distances.
It's like the universe is playing a game with rules we're still figuring out.
It's mind-boggling, isn't it?
And it reminds us that even our best theories have their mysteries. Professor Levitin also talked about some other big unsolved problems in physics, like dark matter, dark energy, the unexplained values of fundamental constants in the Standard Model. It's a reminder of how much we still don't know.
Absolutely. The stuff we can see, the matter and energy we can explain, is just a tiny fraction of what's out there. The Standard Model, it's a great theory, but it's got holes. We don't know why particles have the masses they do, or why the Standard Model has the specific structure it does. We're missing pieces of the puzzle.
It's exciting, though, right? All these mysteries waiting to be solved.
Oh, absolutely. It's what keeps science moving forward.
Okay. So, Professor Levitin, looking back at your career, decades of groundbreaking work, what would you say has been your favorite area of research, a project that really stands out?
He immediately said his early work in quantum information theory. He talked about his first paper on the topic, published back in 1963 in the Soviet Union. Back then, it was tough to share his ideas internationally. He told this great story about being forbidden from contacting J.P. Gordon, another pioneer in the field. The reason? Gordon was labeled a shark of imperialism. It's funny now, but it shows how politics could interfere with science back then. Despite all that, his early work laid the foundation for the field we know today. It's clearly something he's incredibly proud of.
It's inspiring to hear that kind of passion, even after all these years. Professor Levitin, thank you so much for sharing your insights and experiences with us. It's been a true honor.
The pleasure was all mine. Truly a fascinating conversation.
So, as we wrap up this deep dive, one theme really sticks out: how interconnected everything is. Gravity, computation, information, ideas that seem abstract, they have real-world consequences. And science is constantly testing and refining these ideas, pushing our understanding further.
What's amazing is how these fundamental concepts force us to rethink our assumptions about the universe.
And that brings us to our final thought for our listeners. If we still have so much to learn about dark matter, dark energy, the foundations of quantum mechanics, what other incredible discoveries are out there waiting for us? What seemingly impossible things might become possible? The quest for knowledge never ends. There are always more aha moments to be had. Thanks for joining us on this deep dive.
It's been a pleasure.
Until next time.